Every machine, every room, every factory floor is constantly telling you something. Temperature climbing, humidity shifting, pattern forming in real time. The question was never whether the data exists. The question is anyone actually listening to it? What if the answer to that question was an AI agent running entirely on your local machine? Hello everyone, I'm Hariharnath and welcome to IoT Frontier. Today we are diving deep into multi-sensor AI correlation agents. In this project, we'll be utilizing the sensors from a motor. So for that, the different sensors that we'll be using are real DHT11 sensor for temperature and humidity with ESP32 that I have, and some of the other sensors that we are going to simulate are vibration and power draw directly on ESP32, and these are correlated to the real temperature sensor. So the AI agent sees realistic multi-signal data. So this is episode 2 of Local AI Meets IoT series. Let's get started. So if you see the data flow diagram here, we have a motor, and this motor we are going to read three different values. One is the power, second is the vibration, and third is temperature and humidity. So this is directly connected to ESP32 via a physical DHT11 sensor, and some of them are simulated on ESP32 firmware code. And then we are sending this data to the MQTT broker, and that will in turn be subscribed by the Python program, and this Python will be communicating with Gemma 4 AI model which is running on your local machine. So first we'll try to connect our ESP32 with the DHT11 like this. And the reason why we are using this hybrid sensor strategy is this is like hardware in loop simulation. Engineers use it constantly when physical sensors aren't available. But the control logics need to be tested, so we are doing it legitimately and we'll label it clearly in the firmware as well. And if you can see, the vibration is directly correlated with temperature here, and this is how vibration will be affected when the temperature is raised. And the power is also directly correlated with the temperature, and this is how we can call it as hardware in loop, and we are using mathematical logic to say that whenever temperature climbs, vibration and power draw also climb with it, so that we can simulate the overheating motor. And the AI agent also sees all the four signals moving together and can reason about the correlation. Now let's start with the hardware layer. So as we have connected this, so once you have connected this DHT11 connections, you can connect your ESP32 onto your laptop via USB, and then you can open this Arduino IDE. And the first thing that you need to do is you need to make sure you have this additional boards for ESP32, and this is the JSON that you need to provide for additional boards so that you can program ESP32 with this Arduino IDE. So once that is done, you go to board manager and search for ESP32. So you need to install this ESP32 here. So later on you can select the boards from here. So I'll select this ESP32 dev module, and the COM port should be available here. And this is the program that I have created for multi-sensor. So here the major things that you need to do is you need to modify the MQTT broker which is running on your laptop. So that we will be doing in the next step. So before that, you can simply open a command prompt and type ipconfig, and you can find the IPv4 address, that is 29.152. So I just pasted that here, and the Wi-Fi SSID and password of your house, so you can use that here. And we can see the hardware we are connecting with this sensor DHT11, and we are trying to install PubSub client, Wi-Fi, and other libraries that we need to install is DHT sensor library. So in the library manager from here, you can type DHT sensor. So you need to install this DHT sensor library by Adafruit, and you also need to install Adafruit unified sensor. So this PubSub client you need to install, and Arduino JSON. And if you go to the code further, you will see there are some simulation baselines. So you can see the baseline temperature we have kept it 25, and vibration as 12 Hertz, and the power draw is like 85 watts. This would be like a healthy motor with these values. and then we try to use some noise, simulate some vibration. As I mentioned about the correlation values, like we are going to create a vibration using the baseline temperature. Same way for power also we are simulating with baseline temperature and the real temperature. And we connect to Wi-Fi and MQTT, and in the setup you can see the MQTT is connected in the loop. So we are trying to simulate the vibration, power draw, etc. And then we are going to serialize them into JSON and then publish it into MQTT client. So now because we have connected our COM3 port to this ESP, you can simply click on upload. So it will complete the upload of this firmware. So in the meanwhile, we can go to the mosquitto.org. So here we can see mosquitto.org. You can download Windows version here, and I have already downloaded and installed it. So once you have installed Mosquitto, you can see the path should be C program files Mosquitto, and here you need to do few things. That is the mosquitto.conf, the configuration has to be set properly. So you can open with Notepad or ++. So first thing is listener 1883. So you need to enable this 1883 to be as a listener. And second thing is anonymous. And we need to make sure we are using anonymous as true, because this is just a POC or a demo that we are using. But in the real production, you should not use anonymous. So using this anonymous refers to you don't have to provide any kind of username, password and additional authorization. So once the configuration is done, there is another thing that we need to do. That is, you need to go to Windows Defender Firewall and allow the inbound port of 1883 to be open. So go to advanced settings, because we are going to get the MQTT messages from your ESP32 onto your laptop where the MQTT broker is running. So you need to enable it. So go to inbound rule, you need to click on new rule, click on port, next TCP, and the port should be 1883. Click on next, allow the connection, next, and give the name as MQTT. So I have already done it, so I'll just cancel it. Once you do that, you can simply check that somewhere should be available like this. So these are the two changes we need to do before you start the Mosquitto broker. So once that is done, you go back here and simply open a terminal in that folder. And then here you need to start Mosquitto with this configuration, and we can see it is listening to 1883. And because we have already started this ESP32, you can also see the values that until now MQTT was not running. When we just started MQTT broker, you can see it is trying to send the messages. So the message will be like this format. So what is the device ID, temperature, humidity, vibration, on all the values we can see here. And the same messages will be read here, and we will not see the exact message here, but we are going to see whether the publish is happening in the broker or not. And we can verify with MQTT Explorer. So you can simply download MQTT Explorer from this page, and I'll open MQTT Explorer, and here you need to click on plus connections. So I need to provide the host like 192.168.29.152, and in the advanced you can simply delete, and you can provide the topic that you are using. So I'll copy the topic. So this is the topic, and paste it here, go back and connect. So you should be able to see the messages here. So in the sensors you can see the message, and what is the change also you can see here, and you can see how many messages that are coming. Every 5 seconds these messages will be changing. So which means that our ESP32 is sending properly all the messages. So I'll disconnect this first. So now we'll try to create a Python agent. So for that we have to create the folder. So this folder was already created, and then I'll just get into this folder and I'll create the virtual environment and then activate into that. And after that I'll just install some of the important libraries, that is PAHO MQTT for MQTT client and Ollama that we are going to use for AI. So now we are done with this. So what we'll do is we'll download Ollama. So in the previous episode we have downloaded Ollama already. And if you haven't downloaded, you can go to ollama.com and click on download and download it first. So once you have installed the Windows version, you can just go back to the models and search for the model which we want to use. And in this project, we are going to use Gemma 4. So this Gemma 4, we can click on it. So this is the latest frontier model by Gemini. So here, if we want to use the latest version, it is like 9.6 GB. So you have to just copy this and type Ollama run Gemma 4. So for that, I'll try to open another command prompt and type Ollama. So it will download and then run this Gemma 4. Because this is 9.6 GB, it will take some time. So I've already downloaded for the sake of this tutorial. So it should automatically run. So you can see this is running. I'll simply close this. So next thing is we need to start this Python agent code. So we can simply write code agent.py. So it will open the Python file. So this is the Python file, and the few things that you need to change is the local host should not be there. It should be your IP address, as well as I'm using Gemma 4 latest. So based on the Ollama model that you are using, you can simply replace this. And here you can see the baseline, how the healthy motor should look like and what are the thresholds. So here we have kept the thresholds like 35, 80, 18 and 110 for each of them. And these, whenever 4 of them happen to be deviating, then we have this AI that will be monitoring it and giving us the analysis. So what majorly this Python code does is, first, the trigger logic is correlation aware. So it is not just this threshold based, it fires when multiple signals move together, not just when one crosses a line. And second, the prompt engineering gives Gemma 4 explicit context. So you can see that. So this is how we give the prompt, that these are the current readings, this is the baseline, and what is the analysis that it has to give. And based on this, it will find what the trend has been over last 5 readings, and the context is what produces the bearing wear diagnosis. Third, the agent runs smart. It doesn't call Gemma or AI model on every reading. It calls it when something interesting is happening, so that it keeps the response times low and the terminal output clean. Because you can see the exponential backoff, we are trying to make sure that it is only calling whenever it is needing. So generally what happens is, once the motor crosses a threshold and stays there, every 5-second reading would trigger a fresh Gemma 4 call. If motor runs hot for 2 minutes, that's exactly 24 LLM calls printing nearly identical analysis. So it will be noisy, wasteful, and in a production deployment, it hammers your inference server. That's why we have kept alert cooldown manager. So next thing is, we need to simply run this code. So I have saved it, and now I can run python agent.py. Now we'll try to look into different scenarios. The first thing is, our sensor is in a normal temperature. We can see the response that all the signals are nominal. So now we can try to increase the temperature by putting this sensor on top of a candle, or you can use your hair dryer. Now I try to put the sensor above the candle. So you can see the temperature is slowly rising. And whenever we saw that the temperature has gone above the correlation trigger, so you can see it has gone to 35 degrees. And now, because all the values are more than the correlation trigger that we have mentioned, so you can see it is calling the LLM. Now you can see the response from this Gemma 4, because my laptop might be slower, you can see the response got in 48 seconds. But if you use higher GPU versions, then you might see the response quicker. So we can see the warning. This is the LLM analysis that we got. So it is saying that the significantly elevated and fluctuating power draw coupled with rising motor temperature indicates increased electrical resistance and mechanical stress. This pattern suggests the motor is operating under severe overload condition, potentially due to bearing friction or mechanical binding. So it is asking us also to inspect the motor load coupling and check for internal resistance buildup or component binding. So after that, you can see there is multiple backoffs, because we have put a cooldown alert manager. So it is trying to check whether this is happening continuously, so it will not allow. And later on, if you see, after some time, the cooldown will be reduced. Like it will be only for 10 seconds as we mentioned. So after 10 seconds, it will be again allowing, and we'll see similar kind of response from the LLM. And now we can see the temperature is kind of reducing. So I'll make it more cooler. So you can see the cool down remaining is now increased to exponential time. So previously it was 10 seconds and now the cool down has become 40 seconds. So until that, it will try to check whether correlation is happening or not. We are still seeing that correlation is happening. Now that we can see it is below 35 degrees Celsius, you can see the correlation is also switched off. All signals are now in nominal position. You can see these values in our code. So you can see this is the baseline that we have allowed, and by which the reference values will be taken, and this is the threshold. Like if it is more than 37 degrees, it means it is a critical condition. But now we have put a correlation trigger which is not just about thresholds, which is about the multiple values. For example, these are the 3 different values, temperature delta. So this is 30, and delta means how much is the above baseline. So we have put 5, which means 30 plus 5, 35. Whenever you reach a value above 35, this correlation trigger occur and LLM will be red. And same way for delta of this vibration, that is 2, and power also it will be like this, 16. So basically there are 2 checks. First is correlation trigger, and after that, if it still reaches above 37 degrees or 80 or 20, 130 here, then it is a critical. So this is like a warning and this is like a critical value. Now that we have seen the warning, we'll try to look into the critical. So we'll make sure that our temperature will be reaching more than 37 degrees. Because it got into this correlation analysis, we'll look into the Arduino IDE to check the latest values. So now you can see here 38 degrees has come. So we'll just wait for correlation analysis to be complete. So once you can see this correlation analysis is done, you can see the temperature was above 37 degree, that is 42 degrees. So which means that it is very critical condition. Previously it was warning, now it is critical, and now it is again calling the LLM, even though previously we have called the LLM. Which means from warning to critical, it will not ignore the critical value, because we have kept the backoff, that is exponential backoff, will smartly behave that it has to call the LLM. So you can see now we got a similar kind of response. And you can find all these firmware, Python agent and setup commands from the link in the description, and everything is copy paste ready so that you can replicate this project. What we built today is something you cannot build with simple if and else block with thresholds. A simple temperature sensor firing at 35 degrees tells you something is hot. 4 correlated sensors moving together, that is temperature rising, vibration climbing, power draw increasing, tell you a bearing is failing. That's a completely different category of intelligence. In episode 3, we are going to plug InfluxDB directly into this pipeline. Every reading our sensors published or stored, timestamped and queryable. And then we are going to give Gemma 4 the ability to reach back into that historical data and reason across it. That's where predictive maintenance actually begins. And it runs on the same local machine where your LLM is running. If you want me to work on next episode, then drop the word InfluxDB in the comments. If you found this video informative, please subscribe and hit the bell icon. If you want to learn IoT from scratch, check out my course on Udemy. Thank you for watching, and I'll see you in another interesting video.